morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about USART, that is 8251 Universal Synchronous Asynchronous Receiver Transmitter. In this class, we are going to discuss the architecture, pin description, and various control register formats we will see. These slides are prepared by referring the textbook Advanced Microprocessor and Peripherals, authors IARE and Budchandi, publication Tata McGraw-Hill. 8251, which is USART, is a universal synchronous and asynchronous controller designed by Intel basically to facilitate communication. USART stands for Universal Synchronous and Asynchronous Transmitter, Receiver and Transmitter, and functions as an intermediary that follows serial and parallel communication between the microprocessor and the peripherals. This USART converts serial data to parallel form and vice versa. That is, parallel to serial data conversion also takes place. It allows both synchronous and asynchronous transmission and reception. The block diagram or architecture of 8251 USART is shown in figure 1. Here, this is the internal bus, which is used for data transfer between one block to another block. The various blocks present in 8251 are data bus buffer, read-write control logic, modem control, transmit buffer and transmit control, receiver buffer and receiver control. We will see one block and what is the functionality and the significance of the pins corresponding to that particular block. The first one is a data bus buffer. It is basically an interface, the 8251, with the internal system bus of the processor, that we can take as system bus. The data bus buffer has an 8-bit bidirectional data bus that allow the transfer of data bytes, status or command word between the processor and the external devices. The second block is a read-write control logic. This functional unit generates a control signal for the operation of 8251 according to the signals present in the control bus of the processor. Basically, it performs a decoding operation of control signals produced by the processor so that a respective operation can be performed by the USART. The control formats for system operation is stored in control and command word register present in this USART. The various control signals which are present in this read-write control logic unit are CS bar, which is a chip select act to low signal. As bar indicates it is a act to low signal, indicates whenever CS takes 0, the signal is said to be active. This chip select is used for enabling the 8251 in order to communicate with the peripheral devices. The next pin is C by D bar. As the system has control, status and data register, this pin indicates whether it is a data information or control and status register information. If C by D bar is equivalent to 1, it indicates it is control information. This control information means it is used for controlling the data flow between the peripherals and the processor, as well as functional, how it has to be function, what are the various modes to be operated, that will be decided by this control information. When C by D bar is equivalent to 0, then the information on the data bus is the data which we use for transmitting the data or received data which is present on the data bus D0 to D8, which are connected to data bus buffer. The next signals are read bar and write bar. These are active low signals, which is for indication or status signal for both a read and a write operations. The next one is clock signal. It produces the internal timing of the device. At what rate the function has to be takes place, that will be decided by clock frequency. Reset, it puts the USART 8251 in the idle mode. The next block is a transmit buffer. This unit is used to change the parallel data received from the CPU through data bus buffer into serial data which has to be transmitted through TXT line. In order to transmit the serial data to external devices, it is provided with TXT pin. So for the transmit buffer, the output is a TXT line. The data will be get from the processor, which is of 8-bit size, and the data is going to be transmitted serially. Whereas the input data is a parallel data, so it will convert the parallel data into serial data. This unit consists of 2 registers. They are as follows. Buffer register, basically the data provided by the processor is stored in the buffer register. Further, this data is fed to the output register. The second register is output register. This register changes the 8-bit parallel data into a stream of serial bits. Then this data is provided at the TXT line pin so as to transfer this data to the peripheral device serially. The various control signals are attached to the transmit controller. It controls the transmission action. The various control signals generated by this unit are as follows. TXRDY. This signal implies the transmit ready. So it will give the status of the readiness of the transmitter. This signal is used to notify the processor that the buffer register of 8251 is empty and ready to accept the data so that it can transmit on TXT line. The next signal is TXE, which stands for transmitter empty. It indicates that the output buffer is empty. So whatever the data which is sent by the system to the transmit buffer, that is transmitted through TXT line. The emptiness of the output buffer or output register will be indicated by TXE line. TXE bar, this stands for transmitter clock. It controls the rate of character transmission by the USART. The next block is receiver buffer. This unit takes the serial data from the external device, changes the serial data into the parallel form so that it can be accepted by the processor. So for this receiver buffer, first the data will be received in RxD line. As the data is received serially, this will be buffered here. Once all the data is collected here, this data will be transmitted to the processor on the data bus lines D0 to D7, which is 8-bit size. So the receiver buffer, the input is a serial data and the output is a parallel data. So it can be used as a serial to parallel conversion. When the external device is ready to send the data to the 8251, then it sends a low signal to the RxD line of 8251. Once the data is received by the receiver, the input register, then it is converts the data bits in parallel form and send it to the receiver buffer register. Receiver control. This unit controls the operation of the receive buffer. It manages the data reception. Along with that, it also detects the presence of false start bit, error in parity bit, framing errors, etc. So when the data is receiving, there are three types of errors can be occurred. One is parity error, frame error, another one is overflow error. RxRDY. It stands for receiver ready, which indicates that the receiver buffer register is holding data and is ready to transfer to the processor. Next, RxC bar, which is a act-to-low signal. It stands for receiver clock, controls the rate at which the 8251 receive the data in the synchronous mode and asynchronous mode. During asynchronous mode, the signal synchronous detect or break detect will indicate break in the data transmission. During synchronous mode, the signal synchronous detect or break detect will indicate the reception of synchronous characters. The next block is modem control unit. The modem control unit allows to interface a modem to 8251 and to establish a data communication through modem over telephone lines. This unit takes care of handshake signals for modem interface. The control circuitry for handling various signals is provided by the modem control unit. It includes DTS, RTS, DTR and CTS. DTR is data terminal ready. DTS DSR, it is data set ready. RTS, request to send. CTS, clear to send. First we will see the DSR signal. It stands for data set ready, and the signal is used to check whether the data set is ready or not when the processor is in the urge of communication. The next signal is RTS. It stands for request to send. A low signal shows an assertion of data transmission. CTS, this is also act-to-low signal, clear to send. When 8251 receives a low signal at this pin, then it clears all the data present in the modem in order to allow further communication. DTR implies data terminal ready, shows that the 8251 is now ready to accept the data from the processor. The pin description of 8251 USART is shown in figure 2. D0, D1, D2, D3, D4, D5, D6, D7 are 8-bit data bus which is used for interfacing the system bus of 8086 with the internal data bus of 8251. RxD line, which is receive data. GND and VCC are the necessary power supply required for biasing the internal elements of 8251, which is a transistor for biasing. TXE, it is a transmitter clock pulse. Write bar, the status signal indicating the processor wants to write some data to 8251. CS bar, to enable 8251, we have to make this pin as low. C by D bar, it indicates whether the information on the lines D7 to D0 is control information or data information. If C by D bar is equivalent to 1, it is control information. If C by D bar is equivalent to 0, it is data information. Read bar, it is a status signal indicating the processor wants to read the data from 8251. RX RDY, which is a readiness or status signal by the receiver indicating the receiver is ready. RXC bar, it is a clock pulse for the receiver. At what rate the data has to be received will be decided by RXC line. DTR, it is for modem control signals. Data terminal ready. Request to send. Data set ready. Reset, this signal is used for to bring 8251 to a unknown state or ideal state. Clock, this will give the clock pulses necessary for operating 8251. TXT, transmit data. The data will be transmitted serially through TXT line. TXMTY, this is indicates whatever the data which the processor sent for transmission has done through TXT line. So once the data is transmitted through TXT line, the transmit buffer will be empty. That emptiness will be indicated on this line. CTS, it is modem control signal which is clear to send. Synchronous detect or break detect, it is for indicating in the synchronous communication detection of synchronous character. In asynchronous communication, it is for detection of break. TXRDY, this signal is a status signal of the transmitter indicating the readiness of the transmitter. For programming, the USART, which is 8251, have few register internally which we have to program to operate for serial communication through USART and system. There are two types of control register. One is mode instruction register, which is used for setting the functionality of USART. The second one is command register, which is for setting the USART for operation. There is one more register which is status register. The status register is always read by the processor. Processor is not having any write permissions to the status register. Whereas these two registers, the processor will write the data into these registers. The processor cannot read these two registers. So for these two registers, write permission will be there. For the status register, read permission will be there to the processor. Now we will see the first register, which is mode instruction control word. The mode instruction is used for setting the function of the 8251. After resetting will be recognized as a mode instruction. Items set by mode instructions are as follows. To configure the 8251 either in the synchronous mode or asynchronous mode. How many stop bits we have to send in the asynchronous communication. What is the length of the characters? What is the size of data which you want to transmit or receive? The various sizes which the data can be transmitted are 5 bits or 6 bits or 7 bits or 8 bits. The next one is parity bit, whether we have to enable the parity bit or discarding the parity bit. And if the parity bit is enabled, what kind of parity bit we have to send? Either it is even parity type or odd parity type. The next one is for asynchronous communication. What is the baud rate factor? Next, internal, external synchronization for synchronous mode. How many number of synchronous characters we have to send in the synchronous mode? The format or bit configuration for mode instruction control word is as follows, shown in the figure 3. The last 2 bits indicates as it is asynchronous communication. Baud rate you can set as 01 or 10 or 11. If you select these 2 bits are 001, the baud rate factor is 1x of the clock. If you select this one as 10, the baud rate is 16. Baud rate factor is 16. If you select this bit as 11, the baud rate factor is 64. The next two bits are corresponding to what is the character length, how much amount of data you want to transmit or receive. If you select these two bits as 00, 5 bits of data, 01, 6 bits of data, 10, 7 bits of data, 11, 8 bits of data. The next bit is corresponding to whether to enable the parity bit or not. So if you write this bit is equivalent to 0, the parity bit will be disabled. No need to include the parity bit for the transmission or receiving. If you write this bit is equivalent to 1, the parity bit we have to include for transmission. At the receiver side also we have to receive the parity bit. If the parity bit is disabled, the next bit is a don't care. If the parity bit is enabled, there are two types of parity bit we can have. Either it is even parity or odd parity. This bit is corresponding to PE or EP. So if you configure this bit is equivalent to 0, odd parity. If this bit is equivalent to 1, the scheme which we are using is even parity type. The last two bits are used for indicating how many bits we need to add for stop bit in the asynchronous communication. 00 is a invalid case. 01, 1 stop bit. 10, 1.5 bits. 11, 2 bits. Here, 1 bit, we are aware of 1 bit and 2 bits. But 1.5 bit means the stop bits, how many clock pulses we have to send. For how many clock pulses we have to send. If the stop bit is transmitted for only 1 clock pulse, then it is called as the number of stop bit is equivalent to 1. If the stop bit character, if you are sending for 1.5 clock pulse, then it is 1.5 bits. If the stop character you are sending for 2 clock pulses, it indicates the number of stop bits are equivalent to 2. So 1.5 bits is not indicates the size of how many bits we are sending. The stop character for how much duration we are sending. Either it is for 1 clock pulse or 1.5 clock pulse or 2 clock pulses. Next, the mode instruction control register for synchronous communication. The figure 4 shows the bit configuration of mode instruction for synchronous mode. As we are selected for synchronous mode, the last two bits, the baud rate is synchronous, so we have to write these bits as 00. The next two bits are indicates what is the character length. 00, 5 bits, 01, 6 bits, 10, 7 bits, 11, 8 bits. The next bit indicates whether to enable the parity or not. So if you configure this bit is equivalent to 0, the parity bit will be disabled. If you configure this bit is equivalent to 1, the parity bit will be enabled. If the parity bit is enabled, what kind of parity we have to take? Either it is odd parity scheme or even parity scheme. The last two bits indicates stop bits will not be there. It will indicate how many number of synchronous characters we have to send. How many number of synchronous characters we have to send. 10 for 1 synchronous character. Next one is 2 synchronous character. The next register is command register of 8251 of USART. Command register is used for setting the operation of 8251. The items to be set by a command register are as follows. Transmit, enable or disable. Receive, enable or disable. DTR, RTS, output of data. Resetting of error flags. Sending to break characters. Internal resetting. The last one is hunt mode and it is used for synchronous mode. The table 1 gives the description of each and every bit of command register. TXE, it is for transmit enable. If you configure this bit is equivalent to 1, the transmitter will be enabled, otherwise the transmitter will be disabled. To enable the data terminal ready, we have to configure the DTR signal is equivalent to 1. RXE it is for receiver enable. To enable the receiver, we have to configure this bit is equivalent to 1. If you configure RXE bit as 0, the receiver will be inactive state. SBRK, it is for send break characters. In asynchronous communication, we need to send the break characters. So for that, we are going to be enable SBRK. ER, it is for clearing the errors. The type of errors which are occur is three types: frame error, over error, and parity error. So if any error is occurred, if you want to clear those error flags, then we have to write this bit is equal to 1. RTS, a request to send. IR, it is for internal reset. For internal resetting, we have to enable this pin. EH, it is for to enter into hunt mode. The next register is status register, which can be accessed by 8251. So only read permission will be there on this 8251. It is possible to see the internal status register of 8251 by reading a status word. The table to describe each and every bit of the status register. The bit 0, which is a transmitter ready. So for transmission, first we have to check whether the transmitter is ready or not. So for that, we are going to read the status register and check the LSB bit whether it is 1 or 0. If it is 1, the transmitter is ready. If it is 0, the transmitter is not ready for transmitting the data. Bit 1, it is for receiver ready. By checking the status register for this bit, we can know that whether the receiver is ready or not. If RX RDY is 1, it indicates the receiver is ready for receiving the data so that the processor can read the data from the buffer. TXMTY, it will indicate the emptiness of the transmit buffer. So once the data is transmitted on the line TXT line, all the depending upon the size of data which was selected in the mode instruction control word, all the data, if it is transmitted, then the transmitter empty. So whenever this signal is equivalent to 1, it indicates the transmission is completed. We said there are three types of errors. One is parity error. So whether the parity error is occurred or not, we can check by checking the bit 3 of the status register. If P is equivalent to 1, it indicates there is a parity error. Next bit is OE, which is overrun error. So whenever any overrun or error is occurred, then this bit will be set to 1. FE, it is for framing error. If any frame error is there, then this bit will be set to 1. Next, synchronous detect. So whenever a synchronous character is detected in the synchronous communication, then this bit is going to be 1. Data set ready. So whenever you are communicating through the modem, if the data set ready is active, then it will be reflected on DSR. Now we will see what are the various types of errors can be occurred. For receiving the data, we have to check all these 3 bits. If all these 3 bits are 0, 0, 0, it indicates the valid data is received. If any one of these 3 bits are equivalent to 1, it indicates there is some error in the received data. So either error may be occurred due to parity or overrun or framing. If any one error is occurred, then the data whichever we have received, it is not a valid data. The various errors definitions we will see. The first one is a parity error. At the time of a transmission of data, an even or odd parity bit is inserted in the data stream. At the receiver side, if the parity of the character does not match with the predefined parity, then the parity error will occur. The next one is overrun error. In the receiver section, received character is stored in the received buffer. The CPU is failed in reading the character loaded in the receiver buffer. The next received character places in the previous one and the overrun error occur. So before capturing the data by the processor, if the second data is sits on the receiver buffer register, then this overrun error will occur. The last one is a framing error. If valid stop bits is not detected at the end of character framing, error will occur. So okay, with this I will conclude. The references which I have referred is AARE KM Butchandi, Advanced Microprocessor and Peripherals by Tata McGraw-Hill publication. Next one is a few contents I have referred in the website electronicsdesk.com_8251-USART.html, and the pin diagram I referred in the YouTube site. So I referred youtube.com/watch V is equivalent to N90UOB4-FDK. So in this lecture, we have discussed what is 8251, what are the features of 8251. 8251 is a USART. What is USART stands for? Universal Synchronous Asynchronous Receiver Transmitter. How the data will be transmitted through USART as well as how the data will be received by USART. We have studied the architecture of 8251. We have discussed the pin diagram of our signal description of 8251 is also studied. Then the various control registers of 8251 like mode instruction, control register, next command control register, status registers, the bit description of each and every register we are discussed. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.